This video recording will explain to you how to apply the Hopital rule to the indeterminate form of the type infinity over infinity. Suppose the function f and g are differentiable on an open interval containing the point x equal to a, except possibly at x equal to a. And then suppose the limit of f of x when x approaching a is equal to infinity, and limit of g of x when x approaching a is also infinity, if the limit of f prime over g prime as x approaching a exists, or if this limit is plus infinity or minus infinity, then according to the Hopital's rule, limit of fx over gx when x approaching a is equal to limit of f prime x over g prime x when x approaching a. Moreover, this statement is also true in the case of a limit as x approaching a minus, x approaching a plus, x approaching minus infinity, or x approaching plus infinity. Here is an example of how we apply this Hopital rule. I want to find the limit of x over e power x as x approaching infinity. So this problem is actually of the type limit of x goes to infinity fx over gx. Now, where f of x is equal to x now, g of x is equal to e power x. And we know that the limit of x goes to infinity of f of x will be infinity, and limit of x goes to infinity of g of x, which is e power infinity, also infinity. You can actually see the graph of e power x if you have forgotten. This is the graph of e power x. So when x goes to infinity, you'll find that the y goes to plus infinity. Therefore, we are having indeterminate form infinity over infinity. However, infinity over infinity is not necessarily 1. We can apply the Hopital's rule, and we know that f prime of x is equal to 1, and g prime of x is equal to e power x again. So this is equal to the limit of x goes to infinity, differentiation of x over differentiation of e power x. And I already show you differentiation of x is 1, differentiation of e power x, and we know that the limit of x goes to infinity, e power x goes to infinity. So you have 1 over infinity, and therefore the limit is 0. Let's look at example 3b. I'm going to find the limit of ln x over cosecant x when x goes to 0 plus. So this time we are having a limit of x goes to 0 plus f of x over g of x now, where f of x equal to ln x and g of x equal to cosecant x. Now, we know that the limit of x goes to 0 plus for f of x, which is the limit of x goes to 0 plus ln x, and this is negative infinity. Why is this so? If we recall the graph of y equal ln x, it looks like this. If x going towards 0 from the right, then you find the y going towards minus infinity. As you move the x towards 0 from the right, you find that the value of y goes towards minus infinity. So this is why limit of f of x when x goes to 0 plus is equal to minus infinity. Now how about limit of x goes to 0 plus cosecant x. Now cosecant x is actually 1 over sine x. And we know that when x goes to 0 plus, sine x will goes to 0, but also positive. So this is going to be 1 over 0 plus or equal to plus infinity. You can also see the graph of cosecant x here. This is the graph of y equal cosecant x. You can see that when x approaching 0 from the right, and you find that the y will approach to plus infinity as x approaching 0 from the right. This is why limit of cosecant x when x goes to 0 plus is equal to plus infinity. This is getting an indeterminate form of minus infinity over plus infinity. And what is this equal to? We cannot cancel infinity and say the answer is minus 1. By using the Hopital's rule, this is equal to limit of x goes to 0 plus differentiation of ln x over differentiation of cosecant x. So let's recall, what is the differentiation of ln x? Differentiation of ln x is going to be 1 over x. How about differentiation of cosecant x? If you check the table, this is equal to negative cosecant x cotangent x. So this is equal to limit of x goes to 0 plus 1 over x over negative cosecant x cotangent x. How about the limit now? If you look at 1 over x over negative cosecant x cotangent x, we know that if you look at the limit of 1 over x when x goes to 0 plus, you're going to get 1 over 0 plus, which is infinity. If you look at limit of x goes to 0 plus negative cosecant x cotangent x, you'll find that this is equal to limit of x goes to 0 plus negative 1 over sine x 1 over tangent x. Since cosecant x 1 over sine x, cotangent x 1 over tangent x. When x goes to 0 plus, you'll find that sine x will go to 0 plus. So in the end, you're going to have minus 1 over 0 plus, and then you have minus infinity. Therefore, the limit of 1 over x over minus cosecant x cotangent x will give you indeterminate form minus infinity over infinity again. So this is a perfect case where you still can apply the Hopital's rule. As you apply the Hopital's rule, the differentiation getting more and more complicated because you are going to use product rule for differentiation. So instead of apply Hopital's rule again, we modify the situation a little bit. Let's see how we do without using Hopital's rule. So this is 1 over x over negative 1 over sine x and 1 over tangent x. And I'm going to simplify the expression. This is equal to negative of sine x over x now by multiply the numerator and denominator by sine x tangent x, you have this. So what I do here is actually multiply the numerator and denominator by sine x tangent x, so that when I do this, I have cancellation. in the denominator, and so in the end I have a minus sine x over x times tangent x. And we know that the famous rule, limit of x goes to 0, sine x over x is 1. Therefore, limit of x goes to 0 plus sine x over x must be 1, as the limit from the left and limit from the right must be equal in this case. So you can write them as limit of x goes to 0 plus sine x over x, pull out the minus sign, times the limit of x goes to 0 plus tangent x. This is equal to minus 1 now times 0, because when x goes to 0, tangent x goes to 0 as well. So in the end, the answer is 0. Therefore, the limits of ln x over cosecant x when x approaching 0 is equal to 0. So we only use the Hopital's rule once, because the second time, when you have 1 over x over minus cosecant x cotangent x, although you also have infinity over infinity indeterminate form, you need not to apply Hopital's rule, because I can simplify it. If you apply Hopital's rule, your differentiation will get even more messy. So instead, I simplify the expression and use the result of sine x over x when x approaching 0, the limit is 1. That finish the part of this recording.